Thank you, Paul, for the great introduction. And good morning, everyone. Assalamu alaikum. Today, I'm really glad to be with you to talk about a topic that I'm really excited and passionate about, the Analog Designer's Toolbox, ADT, and how it is going to define a new paradigm for analog IC design. But before I start, I'd like to go back to 1946 when ENIAC, the first general purpose electronic computer, was invented. And the reason I like to show this picture is that when you compare it with the smartphone that everyone now carries in his pocket, you will feel how much tremendous change has happened in the field of electronics in the last 70 years. And this was enabled by two key inventions, the transistor and the IC. And both of them also witnessed exponential advancement in the last decades. So the transistor was shrinked down by orders of magnitude, and the integration density of the IC, the number of transistors on chip, also has increased by orders of magnitude in the last decades. But it is really surprising that despite these exponential changes, the analog IC design flow has almost unchanged since 1970s. Since the introduction of Berkeley Spice in the 70s, actually, nothing has really changed in the analog IC design flow. So we are now using a 50-year-old design methodology. And actually, you can say that 50 years ago, the situation was much better because the designers had simple equations that they can use to analyze and design their circuits. But nowadays, the nanometer transistors have very complex models. So the designers rely on trial and error, multivariable sweeps on the simulation tools, a very tedious, time-consuming process actually that has no designer insight involved. So actually we can say that we don't have a systematic analog design process. And this created a significant gap between the growing chip complexity and the time to market from one side. And on the other side, the designer has limited productivity. So he just tries to get any suboptimal solution. And there is no documentation for the design process and the thinking process. And it is very difficult to transfer the knowledge from the senior generations of designers to the junior generations of designers. So of course, I'm not the first one to talk about this problem. Many people have tried to solve the analog IC design process. And in the 1990s, there were lots of startups, lots of research activity in the universities to do analog design automation. But actually, none of these solutions managed to achieve widespread acceptance in the analog design community. And most of the designers still use the 50-year-old SPICE trial and error methodology. So actually, we tried to do some reflection. Why? Why didn't these solutions manage to address this problem? And we categorized the reasons into 4 categories: technical, psychological, usage model, and business model. And we tried to address these 4 reasons with the solution we are proposing, the Analog Designer's Toolbox. So from the technical side, we are the first analog EDA tool that is based on the GM over ID methodology. And this is coupled with pre-computed lookup tables. So this gives us actually 2 very important benefits: very fast execution time, maybe 100x faster than standard SPICE simulators. And at the same time, we have simulator accurate results. So this is very unique actually to our solution. From the psychological side, we are not trying to replace the analog designers. The analog designers will never be replaced. On the contrary, we are trying to help the designers to be more productive, to make the process more systematic, more optimized, and more fun. And we are also starting with the students because these fresh, bright minds that I am talking actually to today are those who can adopt the new solutions and accept the new solutions and help us make this paradigm change. From the usage model side, our tool is from designers to designers. We created what the designer needs, and we created a very friendly user interface so you can actually learn our tool in less than an hour. And we'll be doing lots of demos, quick start videos to help you actually get the most out of our tool in the minimum time. From the business model side, we are actually offering a very unique actually case in the EDA community. We are offering a free license for non-commercial use. Anyone can download and use our tool. It doesn't have to get our permission. The tool is online. You can just grab your free license and start using it today. And we are also offering a 30-day trial license for commercial use. And overall, we are offering a very affordable and flexible licensing. But before actually I start talking about the tool itself, I need to make a quick revision on some basics. I know that most of you actually are experienced designers, but let's actually revise some of the basics of the GM over ID design methodology, which, as I said, is one of the foundations of our tool. So if we go to the basics, the transistor is essentially a voltage controlled current source. No matter it is a VGT, it is a MOSFET, any kind of transistor, at the end of the day, you have some nonlinear characteristics that governs the relation between a control voltage at one side and an output current at the other side. And the most important parameter actually in this transistor that we care about is the transconductance. And the transconductance is essentially the slope of these characteristics, which gives the relation between the small signal change in the control voltage and the small signal change in the output current. And what makes the transconductance very important is that it is what controls the speed of our analog circuits. So if we take this simple example, the GBW actually is controlled by GM, the transconductance, and it is also what controls the noise of our analog circuits. So no matter you care about thermal noise, flicker noise, or even shot noise, all of them are inversely proportional to the transconductance. So if you think about the transistor as a system, it is actually something that you give a bias current to get a transconductance. Because if you look at these characteristics, if you work at this point, for example, you have a very low slope, so you have a very low transconductance, and you are paying very small current as well. If I want larger transconductance, I need to go to some point like this. Here I have larger slope, so I have higher transconductance, but at the same time, I am paying a higher bias current. So as a system, we can think that we are paying bias current. This is the input that we are giving to the system, and we are getting transconductance. This is the output that we are getting from the system. And the output divided by the input, what we want, divided by what we pay, is what defines actually the transistor efficiency. And of course, in the case of a MOSFET, this IQ is the ID, the drain current, and this what gives us the GM over ID, the famous parameter that we all know. And if we think about the MOSFET as a mathematical design problem, the MOSFET actually is a function of 5 variables. And these 5 variables are 3 terminal voltages and 2 sizing parameters. And the designer has to define these 5 variables for every transistor in his circuit. So how does this happen? First of all, VGS, the most important parameter that controls the current, we actually don't set it directly. We actually set it by the bias current, and then we copy the bias current by current mirrors. So actually this degree of freedom, the VGS, is replaced by the bias current of the circuit, because as we said, the MOSFET or any transistor is essentially a voltage controlled current source. So there is one-to-one correspondence between the control voltage and the bias current. The VDS and VSB are both of secondary importance. For VDS, we just want to make sure that transistor is biased in saturation, and the VSB is usually imposed by the circuit topology. It is not really a designer degree of freedom most of the time. So the designer actually spends most of his time determining these 2 parameters, these 2 sizing parameters, the L and the W, of course, in addition to the bias current. The good news is that when you select the L, the designer can use his intuition. And this is very, very, very important for analog designer to have intuition. This is actually what helps and differentiate an expert analog designer from a beginner analog designer. So when you select the L, you see the trade-offs in your design and the requirements in your design. And if you want, for example, smaller area, smaller capacitance, and high speed, you go and pick a short L. But if you want higher gain, less mismatch, and low flicker noise, you go and pick up a longer L. Actually, the most important problem in this sizing problem is the W, the width of the channel. Why? Because the W is a non-intuitive variable. You cannot select the W by intuition. And I give you an example. If I tell you that for this differential pair, I have a W of 100 micron, what does that mean for you as a designer? Actually, it means nothing. Why nothing? Actually, because this depends on lots of other parameters. It depends on what inversion level are you using, weak inversion or moderate inversion or strong inversion, which translate to what GM over ID do you want, how much L do you use, how much ID do you use to bias your circuit, what is your technology node, is your device a low VT, high VT, so a bunch of parameters actually that affect the selection of W. So as a number, the W is completely meaningless parameter, and it is a non-intuitive variable that you cannot select by intuition. What makes the situation worse is that the search range of W is quite large. So actually the W can range from sub 1 micrometer to 1,000 micrometer, depending on, again, a bunch of parameters. So we actually have a very wide search range, and if you are just doing trial and error, it will be a really painful process. So how did people manage to solve this problem in the good old days? In the good old days, they have a very nice fix, the overdrive voltage. Actually, designers never think about choosing W, but they think about choosing the overdrive voltage, and the overdrive voltage gives them an indication of the inversion level, which actually translates to the efficiency, as we said, the GM over ID. And then they try to calculate some parameters and use this famous square law, the quadratic equation. They plug in numbers here and they try to calculate the W using this equation. This nice fix that was used in the good old days is not valid anymore. Why? Because this simple quadratic law is not accurate in strong inversion, and it is completely meaningless and invalid if you work in moderate and weak inversion. And the overdrive voltage is nowadays a meaningless parameter, and it is not related to the circuit specs like gain, speed, and noise. So actually, we are left without a solution, but the new fix that can help us to fix this problem is the GM over ID design methodology. The GM over ID means that, as we said, what we care most about is this ratio, the GM over ID. So what I need to do is using this ratio as my design knob, using this ratio as my design parameter. So I replace W, I replace the overdrive voltage by the GM over ID, and I think GM over ID. And the great benefit of using the GM over ID as your design knob is that now you have an orthogonal control of the transistor efficiency, which means that if you pick up a specific GM over ID, then you are picking a specific bias point for your device, you are picking a specific spec for your device. No matter you change the bias current, you change the L, the bias point, the GM over ID remains fixed, and in the background, you just look up the new W that guarantees that this is satisfied. So actually, you are selecting a parameter that defines the gain, the speed, and noise, and again, it is an orthogonal control of the efficiency. The good news is that this parameter has a very limited search range. It usually ranges from 5 to 25, as we see in this curve. And the good news, again, is that it doesn't vary from one device to another, from a PFET to an NFET, from a 180 nanometer node or to a 22 nanometer node, and from a low VT to high VT. All of these devices actually have roughly the same GM over ID range, and this range, as we see, is quite limited. So it is very easy for you as a designer to select the GM over ID that gives you the correct specs that you want by intuition. So the GM over ID methodology actually restores the designer's intuition. We are now restoring the designer's intuition because as a designer, you can now think about the specs of your circuit, and then you can select a small GM over ID or a large GM over ID based on the trade-offs that you have in your circuit. So if we summarize this point without wasting too much time, the MOSFET as a mathematical problem has 5 degrees of freedom. The old school replaced the W with the overdrive voltage, and then they used simple equations and trial and error to calculate the rest of parameters. The GM over ID methodology actually replaces both of these, the W and overdrive, with the GM over ID, and then we can use charts and or lookup tables to get all the parameters that we need very precisely with simulator accuracy. So this brings us to the third point in our presentation, which is what is ADT? What is our analog designer's toolbox? What it is all about? ADT is a new analog EDA tool. It is defining a new paradigm in analog IC design. It is enabling everyone to reap the benefits of the GM over ID methodology powered by computed lookup tables. And the goal is to boost the productivity, restore designer's intuition, and make the design process systematic, optimized, and fun. Basically, we are trying to make ADT the new spice. We want to try the way every analog IC designer works and every analog IC design course is taught. And the first feature in our tool is how you abstract your device. Basically, we are abstracting the ugly nonlinear model of the MOSFET in a simple lookup table. A simple lookup table that abstracts this nonlinearity, and you can generate this simple lookup table from our tool in a single click with your own models, so you have full control on your confidential data. And we are supporting both Linux and Windows. So you can use a Spectre on Linux, for example, and you can use a free simulator like LTSpice on Windows. And once you have this lookup table in your hands, you have all the characteristics of the device, and you can start the design process and do whatever you want, from exploring trade-offs and doing your design tweaking without running your simulator again. You just need to run your simulator once per technology to get this lookup table, and then you are done. You can do all your design activity on our tool without invoking your simulator again. So this is our tool, and this is the first feature, the LUT generation, the lookup table generation. So you select your simulator, and as I said, we support both Linux and Windows. And then you give us a reference netlist. And this netlist actually you can generate from your simulator. You can open, for example, your Cadence Virtuoso window, schematic window, and put the devices that you want to characterize. And from EDE, you just export the netlist. And then you give us this netlist file. And from this netlist file, we get all the parameters that we need to build the lookup tables, the LUTs. So you just give us the range that you want to characterize your LUT in, the temperature, the range of device lengths, VGS, VDS, and VSB, the degrees of freedom that we talked about. And we save all the output variables that we need in the design process, the small signal parameters, the capacitances, the thermal noise, the flicker noise, all of this, we save them in lookup tables. And again, this is captured actually across the degrees of freedom. So you capture the nonlinearity of the device, and all of this is done just a single click. You just click a single button, and you have your LUTs built once per technology. And after that, actually, you can again explore all the design possibilities that you want. So the second feature in our tool is the design charts. So if you have used the GM over ID methodology before, so most probably he used some kind of charts. And he used these charts to calculate some sizing parameters or some parameters of the MOSFET that matches the simulator accuracy. We actually make this process very, very much simplified. And we have a very nice feature called the magic cursor that enables you to get data between traces. And you can use this actually to compare the properties of different devices from different technologies at different corners, and take even second order effects into account. So this is how it looks like. This is the device Xplore, what we call device Xplore tab. So you can plot even complex expressions at different settings and compare these expressions together. And this is the magic cursor. You can actually get a point that is off traces, and all of these data are simulator accurate because they are retrieved from the lookup tables, which are generated from the simulator. This is just a snapshot. I will show you a demo, a video in the design examples afterwards. So the third feature in our tool is the design library. I know that most of you in your graduate studies are trying to invent new circuits, because if you don't invent a new circuit, then you will not get your paper accepted. You must do something new in your circuit to get your paper published in a good place. But in the industry, in the real world, you can say that 70% of the time, people are not inventing new circuits. You just pick up a circuit from a textbook or from a research paper, and then they use this circuit in their design project because actually they have very tight timelines and they don't have the luxury of spending 5 years like what you do in your PhD to invent new circuits. So what we are trying to do is that we are building an analog standard cell library. You know, like digital pulse, digital people, they have a very nice thing. They have a digital standard cell library, and this gives them actually the capability to focus on the system level and do all the great things that digital people do on the system level. So we actually need something similar in the analog design flow. So we are creating a standard cell library, and you can select your design from a selection matrix that you will see now. And using a few clicks, you generate a design database. And this design database actually visualizes the whole design space for you, a unique feature that was not available and actually is not available in any conventional EDA tool. So this is our DDB generation tab, design database generation. So you select your circuit class, for example, amplifiers, band gap references, LDOs, and then use this selection matrix to select the type of circuit that you want. For example, type of feedback, type of input signal, type of output signal, the topology, folded, telescopic, simple, what kind of load, what kind of current mirror. So you do your filtering using all these parameters, and then you select the circuit that you want. And once you select your circuit, you can actually generate a database, as I said. And as you can notice here, we don't have W and L. For every device, for M1, for example, we have L and GM over ID. For M2, we have L and GM over ID. We are working in the GM over ID space. We are not working in the W and L space. And this gives us lots of benefits, as I mentioned. So, for example, in this case, I'm generating 100K design points, 100,000 design. If you are doing this using a simulator, it will take multiple hours, and for a complex circuit, it actually may take days. So as you see here, it just takes 2 seconds in ADT. In ADT, in 2 seconds, we generated 100,000 design for this circuit. So what can you do with these huge points of designs? Actually, you can explore your design like never before. You can visualize a design space. You can know what specs are achievable and what specs are impossible. You can add constraints to your design space and see how these constraints affects what is possible and what is not possible. You can do live tuning of your degrees of freedom and see how your tuning point moves in the design space. And you can verify your circuit with your simulator to make sure that what you are getting from ADT is really accurate data with a single click. So this is our design Xplore interface. Again, this is just a snapshot. I will show a video in the design examples. As you see, I can visualize the design space, plot my specs versus degrees of freedom, or plot my specs versus each other, apply constraints and see the design point that matches the constraints, and do tuning and see how the design point moves in the design space. So let's move to the most interesting part in the talk, the design examples. I will start with a very simple example. We'll design a simple intrinsic gain stage that has a single transistor just to get started together. So this is a single transistor circuit. You have some specs here, DC gain, GBW, and CL. And we have 3 degrees of freedom, the bias current, the GM over ID and L. Again, we are thinking GM over ID. We are not thinking WL, we are thinking GM over ID and L. So how can we design this simple circuit? As we said, the GBW, actually what defines GBW is the GM. And again, we have a very limited search range for the GM over ID. So if I put a search range from 5 to 25, I can get an estimate of what bias current do I need in this circuit. So of course, the small current would be in the weak inversion where you have high efficiency, and the large current would be in the strong inversion where you have low efficiency. So we don't have a restriction in this circuit, so we can pick up any GM over ID. Let's say I will pick a GM over ID of 15 in the moderate inversion region. So now I can calculate my current and select a nice number and readjust my GM over ID, and I'm done with these 2 degrees of freedom. So I'm left up with L. How to select the L? This is the first problem. And I also have to select the W. Why? Because the simulator does not understand GM over ID. The simulator needs W and L. So now I need to select the L, and then I need to calculate the W. So let's see how we can do this using the device Xplore. So I basically generated an LUT for my device, and again, this is done once per technology. And now I'm plotting the gain, the intrinsic gain on the y-axis versus the GM over ID on the x-axis. And we have these plots at several channel lengths at several L. So I'll put a magic cursor, and it is a magic cursor because it doesn't have to move on the traces. It can actually move between the traces. So here I put the GM over ID selected 15.71. And then I started tuning my L. And as we said in this example, I want a gain that is higher than 50. So I can get my gain here higher than 50, as we see here, using a channel length of 0.22 micron. And the gain of these values are simulator accurate. Now I need to calculate the W. So how can I do this? You can actually do a simple cross multiplication to get the W that corresponds to the 80 microamp bias current. And you can just plot it here versus GM over ID, and again use a cursor to get your W. And you also have an easier option for you. You can just plot W on the y-axis, but here you use a scale adjustment and you specify the exact current that is passing through the device, 88 micron in this example, and it will give you the same exact curve. So now I'll just put a magic cursor again. I will copy my GM over ID from here, 15.71. And I'm done. I need a width of 10 micrometer. This is in micrometer. So I get my L, I get my W, I got my current. I can go to Cadence, for example, and build a simple test bench like this. This is just a simple trick to set the bias at the high impedance node. And you can see here that we have a very good match between what we got from ADT and what we got from the simulation. The GBW is a bit smaller actually, and the reason is we have ignored the parasitic drain capacitance that is contributed by the MOSFET here. So can we take this into account using ADT? Yes, we can do. Because actually we don't have to plot simple expressions. You can plot a complex expression like this. And as you can see, this is the GBW expression. This is the 1 picofarad load, and this is the drain capacitance. All of this is scaled to the 80 microamp current, and we can plot this expression. We can plot this expression as you can see here versus the GM over ID. So let's see here the GM over ID that we selected and the L that we selected. So we expect here to see the GBW of 196, exactly the same number that we have got from our simulator. But what we need in the design specs is 200 meg. So I just put 200 meg here, and I will get what GM over ID do I need is just slightly larger to compensate for the transistor parasitics. And I can take this new GM over ID value, copy it to the other graphs to get updated values of all my design parameters. So this is a new W that I need to put it in my simulator. And this is my new gain, still matching the spec, and this is the VGS. So also this actually chart gives you lots of insight, because when you increase the GM over ID, the GBW is increasing till it peaks, and then it starts decreasing again, because when you go to weak inversion, the parasitics will increase exponentially, and eventually they will dominate, and then they will bring the GBW down after peaking, as we can see here. So this is our final design. Now we have almost exact match in the game, exact match in the GBW, and as you have seen in just a few clicks, of course, you can never get this using any of the simple models that designers use nowadays. So let's take a bit more complicated example. We will now take a common source example, and this time we will design it using the design Xplore. So let's see how we can do this. We have this common source amplifier, just replace the idle current source with a PMOS device, and we have again some specs on the gain, the GBW, the current, and the area. And from the designer's intuition, we know that for the input device, I need to use a higher GM over ID and a small L. For the bias device, I need to use a small GM over ID and a large L, and you can actually learn these trade-offs from the slides that I have shown previously. So if we take the previous design as a reference point, I need to increase the channel length a bit to compensate for the parallel resistance here. And also I need to increase the GM over ID a bit to compensate for the added parasitics from M2. So let's see how we can see and visualize our design in the Design Xplore interface. So this is the DDB, the design database that I generated for this amplifier. And now I'm visualizing the DC gain versus the channel length of M1. So this chart actually tells you what range of gain is achievable and how this gain depends on your device length M1. And then I can put some constraints here. These are the constraints that I got from my design problem. And you don't have to put these constraints every time. You can just put them once and copy them very easily from one chart to another, from one design to another. So I'm putting my DC gain. I need a gain larger than 50, a UGF larger than 200 meg, a bias current from 50 to 100 microamp, and an area that is less than 200 micrometers squared. So now I will plot using these constraints, and the orange points showing up here are the design points that satisfy my constraints. So all of these actually are valid design points. All of them are matching my constraints. So let's plot some more charts to get some more insights in this design problem. So I'm now plotting the DC gain, but versus the channel length of M2. And again, applying the same constraints, I just copied them from the other plot. And again, these orange points are the points that satisfy my constraints. I go to another plot here. I'm copying all the settings. And here I'm plotting the GM over ID on the x-axis and the UGF, the unity gain frequency, the GBW, essentially on the y-axis. And again, you can see from here, for example, that for this design, I need to use a bit high GM over ID, as we said. For example, if you use a GM over ID of 10, you will never achieve your specs. You have to use the GM over ID in this range to get your specs right. And here I'm plotting actually specs versus each other. So this orange region is what we are looking for. We are trying to get our design point in this orange region to get our GBW spec and our DC gain spec. So how can I tune my design and gain insight into my circuit using Design Xplore? We have a very nice feature here called the tune, when we can do tuning of your design. So these are your degrees of freedom. Again, in the GM over ID space, for every device, you have the L, and you have the GM over ID, and you have the bias current, of course. And here I'm putting the initial design point that I got from the intrinsic gain stage. And this yellow circle is your design point. Okay, so actually it is far from the orange region. I need to bring it here. So I start by increasing the device length of M2, the bias device, the PMOS device. And as you can see, the gain is increasing. But of course, it will saturate because I'm using a fixed L for M1. Of course, this is actually never doable using a simulator, because in the simulator, if you sweep L, you will be changing the bias point of the device. But here we are sweeping L, keeping GM over ID fixed. So I'm keeping my efficiency fixed. And that's why I told you that when you think GM over ID, you have orthogonal control on your transistor efficiency. Because if you sweep other parameters, if you sweep the L, if you see the bias current, you have pinned your GM over ID. It is not changing anymore. So you have a fixed bias point, a fixed efficiency for your device. And as you can see here, I did also a bit tuning for M1. And now I got in the orange region here, I got my DC gain specs right, but the UGF is still not satisfied. Here I have a UGF, all the specs also are updated here automatically. Here I have a UGF of 180, and I need a UGF of 200 meg in this example. So simply, as a designer, you know that to get this spec right, you need to tune the GM over ID of the input device. So I will go to the input device, M1 here. I will start tuning, increasing the GM over ID a bit, and I jumped now into the orange region, and my UGF now is 200 meg. It is now satisfied. So now I got both specs right. I got the DC gain right, the UGF right, and also the area is within the constraints that I defined. So we have also another feature, which is called live tuning. If you don't want to see these arrows, you can just tune your parameters here, and the tuning point will show you live updates. For example, here I'm tuning the GM over ID of the input device. And as you can see, the unity gain frequency is increasing. And as we said, it will peak at some point. And after that, the parasitics will take over, will dominate. So the UGF will start decreasing again after you reach the peak point. So now I am done with my design. I'm satisfied with my operating point. Do I have to go to Cadence to run all these simulations? No, you don't have to do that. You just click verify here. We build the test benches for you. We call your simulator and we parse the results, and we show you here a very simple and intuitive comparison between what we have from ADT and what you have from your simulator. And this green color means that there is a very small error actually between the two. So we have got very accurate results, simulator accurate results using ADT. So someone will say, okay, these are very simple examples. So show me a bit more complex example. Here you go. This is a bit more complex example, a capacitive feedback amplifier, and the OTA is implemented using a folding cascade OTA. And here actually you are trying to optimize two specs simultaneously. You have two objectives. You want the minimum current and you want the minimum RMS noise. So if I go to an expert designer, even someone actually who have designed this circuit several times before, and ask him to analyze this circuit, the analysis is quite tough. We can actually spend a whole lecture analyzing this circuit. And after we analyze it, we will end up actually with some complicated expressions that will give you zero intuition. Actually, you will not have any intuition from these expressions because all the design parameters are entangled together and they are interdependent. So to be very difficult for you actually as a designer to get your specs right, you will actually have to do lots of trial and error to get the minimum current and the minimum noise. And actually, you will never know. You will never know, is this really the minimum current or it is just a good current? Is this really the minimum noise? You will never be sure because the simulator doesn't visualize the design space. But at least as a designer, what we want from you, we don't want you to stop thinking. No, we want you actually to use your intuition. And as we said, your intuition will tell you, so what device do I have to use a large GM over ID? What device do I have to use a small GM over ID? In what direction should I tune my channel length? For example, here, the input pair, you should use the minimum L actually. Why? Because actually, if you increase the L, you will increase the input capacitance at this node. And if you increase the input capacitance, you will decrease the beta, the feedback factor. So we'll end up actually with lower loop gain. So usually we increase the L if we want higher gain. This will not happen in this case because you will end up with lower gain because of the capacitive loading here of the OTA. So let's see how can ADT help you with this design problem. Typical case, if you are going to design this circuit, you will take at least 1 to 2 days, and using ADT, you can get the optimum point in 5 minutes. So let's see how. So I can directly visualize the design space. Here you can see the bias current versus the channel length of M1. So this chart tells you that I need to use a small L for M1. And if you use the minimum L, actually, you will get the minimum current. And also it tells you that as you increase your GM over ID, actually, you need a less bias current. And also it tells you what minimum current is achievable in this circuit. So simply just with this graph, I know that the minimum achievable current for this circuit is around 300 microamp. No matter how much you try, how much you trials and errors, you will never get a smaller current using this circuit. And also there's a very important observation here. All of these orange points satisfy the design specs. So actually, the designer can select some point here with a current of 1 milliamp because he doesn't know that a better point actually exists. He doesn't see this point. He doesn't know about this point because actually he doesn't see the design space. We are trying to give you visualization of the whole design space. You can actually now feel your circuit. You can actually now live in your circuit. So again, all these orange points satisfy the specs, and this is the bias current versus noise space, and I want to minimize both. So I want to get my point here, the minimum current and the minimum noise. So let's see how can we tune this circuit using the design Xplore. So I will now go to select a small L for M1. Tuning point comes here. And then I will select a large GM over ID for M1. So the tuning point will come here. And I can see here that the minimum current is around 300 microamp. So I go here and edit my current, 300 microamp. So the tuning point jumps here. But I still have specs that is not achieved. The bandwidth is not achieved. And also I need to actually fix my phase margin. So let's see how can we tune these two. So I will tune for my bandwidth. And we can see actually the transistor M4 here is a PMOS device, and it adds lots of parasitics at the output node. So if I decrease its GM over ID, I will use a smaller GM over ID for M4. I'm actually boosting my bandwidth, and I got nearer to the orange region that I'm looking for, but I'm not there yet. I need another degree of freedom to tune. So I can go for M3 here. I can try the same trick. I can use a smaller GM over ID, but as you see here, I end up actually with a lower bandwidth because actually for this device is very, very tricky because it controls the Miller effect of the CGD capacitance here. So actually to decrease the Miller effect, you need high GM and high R node from this device. So I go back here to the 15 value and I increase my L to increase the R node. And as you can see, the bandwidth jumped to 106. And I'm now in the orange region, and I got my bandwidth spec right. But the problem is here's with phase margin. I need a phase margin larger than 70, so I'm still not in my phase margin spec here. So I need to use some need to do some more tuning, and also in the noise I can get a lower noise. So I now go to M2 because the non-dominant pole is usually at this node. So again I use a smaller GM over ID here, and again this will help you in the phase margin, will help you in the noise as well, because this device contributes lots of noise, and also this device it contributes lots of noise. So I use a smaller GM over ID for this device as well. And as you can see here, my phase margin now is quite good. And also my noise, I'm quite actually at the Pareto optimal front here. I got almost the minimum current with the minimum noise. So again, I'm now done with my circuit, but how can I know that what I got here is accurate? Just click a single button, just click verify. We go build the test benches for you, and we call your simulator, and we parse the results, and we show you a nice comparison. And you are looking for green color. Yeah, green color, that's great. Yellow color means that there is quite small error, maybe around 10% error, but this is acceptable because you still have you have corners, you have mismatch, you still have lots of variations. So if the error is in the range of 10%, this is quite fine, and you now got your design point right. You got minimum current and noise in less than 5 minutes for a quite complicated circuit. So let's see how we can actually do another very nice thing in design Xplore. We can do topology comparison. The first thing in your design process is topology selection. And we actually help you to visualize the design space so you can very easily compare your topologies. For example, here I'm comparing a telescopic cascode with a 5T OTA. Here I can see what DC gain is achievable for both of them, what UGF is achievable, how the DC gain trades off with the UGF. For here, for the max UGF, I cannot get the max gain. And also this tells me that the output swing, of course, is much better for the 5T OTA, and the phase margin could be problematic for the telescopic cascode. This gives you information about the whole design space, and again, you can apply constraints and see how these constraints affect your circuit. Here is another comparison between telescopic cascode and folded cascode. The telescopic cascode can give you much higher UGF, GBW, almost double the GBW, and also it can give you much higher gain, can give you almost double the gain again. For the output swing, of course, the folded cascode will be superior, so you can easily actually explore your topologies, and you can do this at several technology nodes to compare topology at several technologies, and this is sometimes very tricky using analysis. Using analysis, it is very tricky to compare these topologies, especially when they are near each other, but using the device Xplore and the design Xplore, you have all this simulator accurate data, and you can do all these nice visualizations. I know all of you now will say, but this is all of this is at the nominal point, TT, typical. We haven't shown the ugly part of the process, the mismatch and the corners. And the good news is that we have got you covered. We actually can take corners into account. We can take mismatch into account. This is an example of a very sensitive circuit, the band gap circuit. And the red dots here are from ADT. The blue lines are from the simulator, and you can see we have almost exact match. And this is Monte Carlo simulation, mismatch simulation. And again, we have very good match between what we have from ADT and what we have from your standard circuit simulator. So now we can say, why ADT? After I have shown you all of this, we can see that ADT has unique advantages that is not there in any other conventional ADA tool. We are using the GM over ID design methodology. This gives us orthogonal and confined search space. We have design space, visualization, exploration. We have topology comparison. We actually have 100x faster optimization that I haven't shown in this presentation. We have interactive design tuning, verification, and all of this at 10x cheaper license and even free license for non-commercial use. And we have tested actually our tool with many designers, grad students, and undergraduate students. And we have got very positive feedback. The tool helped them a lot, they liked it a lot, and it was very easy to use, and they were really impressed with the results. So what we are offering actually is a paradigm change in the analog IC design flow. It is not fair, it is not sane to use the 50 years old design methodology. The electronics have witnessed, as we said, tremendous change, and the analog IC design flow needs a change as well. We want to make it more productive, more systematic, more optimized, and more fun. We simply want you to know what you are doing. It is not just a trial and error process. So what is next? You can now Get your tool from our website. You can download it, get your free license, start using it. We want actually everyone to get engaged, and that's why I am with you today, talking with you about our tool. We want to hear your feedback. We want to hear your enhancements, your feature requests. Your feedback really matters to us. So at the end of the day, we want to make you happy. We want to make every designer happy. We want to make the whole analog design community happy. We want to make a change in this analog design community. So thank you very much for your attention. And I'll be glad to answer any questions you may have.